So what they do is to introduce slope fields, I introduce you back to what we used to look at in the day, which was called a family of functions. And the first thing you really heard about a family of functions was in Algebra 2, when we talked about quadratics, and we talked about how you could shift a quadratic up, shift it down, shift it left, shift it right, and open it up, open it down. And we talked about how the parent function was x squared. And then we talked about how the parent absolute value function was the absolute value of x. Well, the parent function, sine and cosine, are the ones that go through the origin or start at 1 and go down. But, so the parent function is up there in black. The purple and the green are simply parts of the family of that function. And what we do when we find slope fields is find those parent functions. So what you'll notice is the original problem was given to you as dy dx equals cosine x. What we did was I used separation of variables. I took the integration of that, and I got y equals the sine of x plus c. I graphed 3 potentials for sine of x plus c. A slope field essentially will give you potentials for families of functions. So let's investigate what I'm saying. So let's investigate seeing these slope fields, seeing how you could get each of these 3 graphs from this right here. So you'll have your family of functions on the top of your page. So let's look at it. What do we know about the cosine of x equal to 0? We actually just talked about it. We said the cosine of x will equal 0 at odd multiples of pi halves. So if you look at the graph that we just created on the previous slide, we can see that dy dx is equal to what? At these odd multiples. So look at the graph. Pi halves. What would your derivative of pi halves be on this graph? The derivative of an extrema. If you look at any of these graphs as pi halves, what's their derivative?
0.
Yeah, not your question. They're all extremas, right? They're all maxes. The derivative of an extrema is 0. So, if you were to look at the graph that we made, dy dx at pi halves would be 0. So how can you tell? Well, you can tell by exactly what I just said. The graph has an extrema at those points. Which means the derivative would be a horizontal tangent, and we know that the derivative of a horizontal tangent is 0. Or the slope, rather, of a horizontal tangent is 0, because the derivative is the slope. algebraically, the y-coordinate does not affect the value of dy dx equals cosine x. Why not? Go ahead.
Like when you derive a constant, it's just 0 anyway, so it doesn't really matter.
Yeah, the up and down part isn't really going to affect me, right? So the up and down does not affect the slope because of exactly what you said. The derivative of the constant is 0. So what that means is the shift that you would see from this plus c is that y value. Well, it's not affecting the dy dx's because its derivative would be 0. So because the derivative of the plus c would 0 out, it does not affect the slope. Does the graph show that the y-coordinate does not affect the value of dy dx? Would you say that you could look at my graph and know that is true? Because what do all of those graphs look like at every point? Would you say that the slope at these 3 points is the same? The slope at these 3 points is the same? Slopes. So can't you see, even though the graph has moved up and down, all of the slopes are the same? So I would say yes, because you could look at the graphs. So again, look, yes, because looking at the x values and comparing the slopes of those values, they are the same. Okay, according to the differential equation, dy dx equals cosine x, what should be the slope of the solution curves when x equals 0? So what that's asking you is, what would dy dx equal when x is 0? So what would be the value of dy dx when x is 0?
1.
Yeah, it's not a trick question. So we're saying that the slope when x is 0 is 1. Looking at your graph, do you agree? When x is 0, does this look like it has a slope of positive 1? Yeah. So the question was, can you see that in the graph? Yes. According to the differential equation, dy dx equals cosine x, what should be the slope of the solution curves when x equals pi? So again, the question becomes, what's dy dx when x is pi? So what's the cosine of pi? -1 is the slope of this graph at pi, and all 3 graphs about -1. Again, there's no x and y lines, so I know it's like kind of harder to see, but can you look at this and be like, yeah, that's probably slope of 1. It's going down. So the cosine x is a what function? Do you remember if it's even, odd, or neither? Cosine is even, odd, or neither? It's even. Okay. So cosine is an even function. Therefore, the slope at any point should be the same as the slope as its reflection across the y-axis. How can you tell? So again, the idea for an even function, remember, are even, odd, and either rules. An even function has that if you put in negative x, you get positive x, but they're the same. So again, if you put in something like, let's say the cosine of negative pi, is that equal to the cosine of positive pi? Yeah. Or you could talk about like cosine of negative pi halves versus cosine of pi halves. They're the same too, right? Cosine of pi fourths versus cosine of negative pi fourths. Both of those would be over here. So you'd have quadrant 1 and quadrant 4. So they would both be positives. The reason we do this with cosine is because its inverse is sine, and it's really nice to see them that way, because you know the graphs of them. But we can use slope fields for lots and lots of different functions. And typically a slope field is a graphical interpretation. Okay. It's a graphical interpretation of what's happening on slopes. So we can take the ideas explored above and use them to produce a graph for any differential. Since dy dx gives the slope at any point xy, we can use the information to draw small pieces of linearization at that point. Repeating this process, we will create, it says a slop field. Did yours say a slop field? Yeah? I lost my E. So create a slop field. A slope field is also known as a direction field. For the first order differential equation, dy dx equals fx comma y is a plot of short line segments with slopes for those points. We also sometimes refer to these as lattice points. If you looked at this, what shape do you kind of see from this graph? Yeah, you kind of see a circle. Anybody remember what the derivative of a circle is? Or could we find it? What? That's the area of a circle. So what's the equation? Okay, let's go back. What's the equation of a circle? You're in geometry. It is. So it's x squared plus y squared equals the radius squared. What's the derivative of this? Don't forget, y's get dy dx stuff. So like, this is cool though, because this is good because your mock exam will have like implicit problems on it. So this is a nice little review for tomorrow. So you have 2x plus 2y, dy dx, and then r, because it's the radius of a circle is typically a number, not a variable. So the r is kind of like a constant, so it would zero out. So we said this looks like a circle. The equation of a circle would look like that, with radius being anything we want. Here would be radius 1, radius 2, radius 3. So its derivative would be 2x plus 2y, dy dx equals 0. Solve for dy dx, because that's what we're talking about, right? This is a differential slope field. So it's dy dx. So you subtract 2x, divide by 2y, you get negative x over y. So this field right here represents negative x over y. If you were to pick a point on this, so let's say we picked the point 1, 1. If you plugged in 1, 1, 1 divided by 1 is negative 1. You see how the slope of that green line is negative 1? Pick another point. Pick, I don't know, negative 3, 2. If you plug in negative 3, negative times a negative becomes a positive, so you have 3 halves. Does this look like it's going at 3 halves approximately? Like up 3 over 2? So these little line segments represent the x and y coordinates for the equation dy dx equals negative x over y. That's how you get those line segments. So you might be given a graph of a differential and you have to figure out what its equation is, or you might be given the dots and you have to make the graph. So you're kind of going forwards and backwards with these. So let's plot our own slope field, because I think plotting it helps you see it and understand it. So it's dy dx equals 2y. Does this match your stuff? Okay. He was flipping back there. I was like, oh no, did I like mess up? So we have dy dx equals 2y. So to find the slopes, you simply plug in points. So if this only has a y variable to it, what's that mean about x? The x really doesn't know. So what that means is that the x is always going to be the same straight across. So like whatever the slope is, so let's say y is 0. What's that make the slope? 0. So everywhere y is 0 is along this horizontal line, the slope of this whole horizontal line is 0. So what's nice is when you only have one variable, it's going to be the same either straight across or up and down. Okay, when y is 1, what's our slope? X doesn't matter, so all of those lines horizontally have the same slope. When y is 2, what's my slope? 2 times 2 is? So the slope is? Remember, this piece of information right here represents the slope in the slope field. So these have to be even more up and down. So if it helps you to see that as a table, it'd be like plugging in the y. And then again, like we said, the x's don't matter because there are no x's on the slope. So these ones would be the opposite of positive 1. They'd be negative 2. These would be the opposite of positive 2. They'd be negative 4. What do we think the original y function would be? So again, you could figure it out too, right? And this is where I said making sure you have the right variables to the right integration variable matters. So here we have dy dx equals 2y. Initially, when you move over dx, it's with a y, and that can't be. So you'd have like dy equals 2 x with that y. You have to move your y over to this side. So in order to integrate these, you have to have the y's with the dy's, the x with the dx. So now when you antiderive, what's the antiderivative of 1y dy? The natural log. And then you get 2x plus c. If you didn't want the natural log on your y, what would you do? How do you get rid of an ln? E. This graph here represents e to the 2x plus c.
Gina Conji and Mitchell Wenzel, please report to the office.
Do we see it? The last, like, part 8 goes with that graph. So it just says, suppose that the point 0, -1 is on a particular solution for the differential above. By following the slope lines drawn in the diagram, what you think that solution would look like. So what they're saying is that this graph contains the point 0, -1. So what we do is we follow the slope field lines. So this line's telling me this graph goes down, and then this is telling me it's going down even faster. So it's kind of like that. This line's coming over to here. If there's a slope of 0 at y, that's going to be like a horizontal tangent line. So it's acting like an asymptote. So this graph would go like this towards that asymptote. And then again, what it's saying is that if we were talking about this function here, -1 equals e to the 0 plus c. Well, e to the 0 is one. I said this is like saying it's equal to -1. -1 equals e to the 0 plus c. What do you know about when you're adding exponents together? It's the same as what? Yeah.
Mrs. McGill, please call extension 201. Mrs. McGill, please dial 201.
So really that's like saying e to the 0 times e to the c. And we said e to the 0 is 1. So it's like saying -1 equals e to the c. So your c value becomes -1. So you could actually use a slope field to find an equation of a. So we already solved it. Like I actually did example 9 with you while we were doing it. I got excited and I jumped ahead. So just put above for number 9. We already did 9. Like 9 is literally the dy dx work I made you do. I just got excited and forgot I made it example 9. So last dy dx example I want to look at is 10. It says construct a slope field for dy dx equals x minus 2y. Why is this one a little bit trickier than the last one? Yeah, we have to take into account both variables when we consider our slopes. So when you do these, I kind of just make myself a little bit of a table, but your table's a little different than what it used to be. Tables used to be plug in x and find y. Well, now we're picking a point x, y, and we're finding dy dx. So one of the easiest points always to pick is 0, 0. So if I plug 0, 0 in, I get 0 minus 0, which is, so over here, the slope of 0 is just a horizontal tangent. Another point, pick, you can stick to picking x's as zeros, or you could, I don't know, say flip it and go to the next way. You could go 1, 0. So we're going over this way. When x is 1, and y is 0, that zeroes out, so you get and then similarly 2, 0. We're going to get 2. So it's just a little steeper. If you went the other way and you did -1, 0, just going to make it go down. And -2, 0 will be slightly steeper and down. Flip it. Let's look at 0, 1. So now the x is 0 out. So x's are zeroed and y is 1. So you get -2. So that means this line slope here should be very similar to the slope I drew here, because this also had a slope of -2. So you just want to try to be consistent. So I want these two to be similarly in their slopes. If I did 0, 2, it would now be -4. So it's just a little bit steeper. 0, -1. Well, what's going to happen? Now you have two negatives, so it's going to become positive. So this slope here is going to be the same as the slope was at 2, 0. Say +2. And this would be a +4. We could pick 1, 1. So you don't have to fill out your table, you're plugging them in. So 1 minus 2 is -1. So again, this point here should have a slope similar to this point here. If you plugged in 1, 2, it would be 1 minus 4, which is -3. So less steep than this, but steeper than that. Two would give you 2 minus 2, or 2 minus 2, 2 minus 4, so it would be -2. And 2, 1 would give you 2 minus 0, or 2 minus 2, which is 0. So it's flat line. Go ahead and finish out your other points. So again, this corner here, they'd be super steep and positive. Over here, your x's are negative and your y's are going to give you negatives. So they're going to be steep but negative, so they're going to actually be the opposites of these. Okay, and down in this lower corner, your x is negative, but your y is negative. So they're becoming a little bit less and less steep. So when you plug in 1, -1, you get -1 plus 2, so you get a +1. Over here, when you plug in -2, you get -2 plus 2, so you have that 0. Down here, you have -2 plus 4, so you have 2. And here we have -1 plus 4, so you have -3, or -1 plus 4, so you have 3. Okay. Once again, if you wanted to solve for it, you would keep the x on the dx side. You would add over the 2y. So this is kind of like implicit differentiation. So you'd have 2y dy equals x dx. and then you find your antiderivative. So this would be y squared equals x squared times a half plus c. So this is kind of like saying y equals plus or minus the square root of 1/2 x squared plus c. And again, if you kind of followed these, you could see along the lines how this would be square roots for x.